Hi everyone, my name is Lydia, and this is what I wish they taught me about econometrics and introduction. We've introduced measurement error and distinguished classical from non-classical. Now, let's begin with the first case. What happens when the dependent variable y is measured incorrectly? This is actually one of the most reassuring results in econometrics. The answer is much better than you might expect. So what is the setup? Suppose that we have the true model. Okay. And we have y star equals to beta 0 plus beta 1 x plus some error term u. Okay. Now, y star is the true value. Okay, that's the true value. But we don't observe this true value directly. Instead, we observe y, which is equal to y star plus some error term. Okay. Now, this E is your classical measurement error. What do I mean? I'm assuming here that expectation of this error is 0. Okay, so the observed value equals the true value plus some random noise. Sometimes we measure too high, sometimes too low, but on average, we measure correctly. So this is the classical measurement error assumption applied to y. The error in here is random, has mean 0, and is uncorrelated with the x or the u error term. So these assumptions are what make the result clean. Concrete example, let's say someone earning 50,000 reports 48, someone who earns 30, 31, and someone earning 40, 41.5. Okay. The errors would be random. Some people report too little, some people report too much. There's no systematic direction. So the classical measurement error in y. Now the question is, if we're studying income, let's say income, as a function of education instead. Okay, so income, we just said that there's a classical measurement error because someone is underreporting, someone overreporting in this case. So we're just making that assumption, though in reality, usually this is the example that you get exactly for non-classical one. But for now, we're just going to assume this is classical measurement error. The question is, does education change? The answer is no. Does the true relationship between education and income change? The answer to that is still no. Does the X move, so your education? The answer is still no, okay? Only the measurement of Y has become noisier. So the X values are exactly where they should be. The regression line is trying to summarize the relationship between X and Y, and X has not been disturbed at all. Now, this is very crucial, okay? It's the crucial symmetry between error in the Y and error in X, or asymmetry, better said. So when error is in Y, X remains clean, okay? Now, we will see a visual representation of that, okay? So if I have this, okay, and let's say the true data, it's in black, okay? This is what the true data would have been. You've got X here and Y. This would have been the fitted line that best describes this relationship. When you are estimating the y with a measurement error. Remember, some y's are going up, some y's are going down, okay? So overall, you could be like, these goes down, and these goes up, and these goes up while these goes down, and so on. So everything is moving a little bit, okay? What changes is that the points now could basically cluster either a bit more loosely around the regression line, but the regression line itself has not changed. Okay, so we've got the same intercept, we've got the same slope. It's just the points now are just dispersed vertically. Okay, and in a sense, the cloud is pended. So if I keep doing more of what I observe, this is where these dots would be, okay? So once again, my fitted line in here has really not changed its position. Because remember, when I asked earlier, does my relationship between income and education change? And the answer was no. Graphically, it means I still have my fitted line exactly where it was, okay? The slope the same, intercept the same, only the scatter around the line has increased. Okay, so the line hasn't rotated. The cloud has simply become noisier. Now, the error measurement E that we have here is entirely in Y. So it moves, so it moves observations vertically, up and down. Okay. And OLS estimates the slope from the horizontal variation in X and how Y responds to him. So since E is random, because remember, we had the on expectation, this is 0, and also that the covariance between your X and E is equal to 0, okay? It means that equally likely you're pushing observations up or down, and it doesn't systematically tilt the regression line in either direction, okay? So the slope averages out the vertical noise, and it still recovers the true relationship between your X and your Y star. So formally, when you substitute the Y in here with the Y star plus E in the actual regression that we are running in here, the term V just ends up as another error, okay? So normally what we would have here is that my Y is the same as beta 0 plus beta 1x plus U plus E, okay? Because I would have substituted this Y star here based on this expression, and I would literally just send this to the other side, okay? So look what's happening in here. There's nothing that has changed on this side. The only thing that has changed is that now I have a bigger error term, okay? For instance, if observations simply move up and down randomly, should we expect the slope itself to change? Most people's intuition says probably not, and that's exactly right, because random vertical noise doesn't tilt the line, okay? And as you can see, we still save that relationship, this beta 1 and this beta 0 in here from the regression that you see. So under classical measurement error, what happens is that the slope coefficient remains the same, okay? So it's unbiased. The intercept also unbiased, okay? However, the things that change and that we have to be careful about are the following: the residual. Remember, the error term became bigger, which means the residual, which is its estimator, is now going to also be larger, And remember, we use the residuals to construct standard errors, which means that also standard errors are going to be larger. And ultimately, R square, it's actually going to be lower because the noisy Y explains less of its own variation. So the cost for this particular type of measurement error is precision, not consistency or accuracy. Okay? So we get the right answer on average, but with more uncertainty around it. Okay? And the lower R square is particularly intuitive in here because R square measures how much of the Y's variation is explained by X. But now Y contains some random noise V and X can't explain the noise, okay? So that's why R square falls. Now, why does this matter? This is actually one of the nicest results in econometrics as we've said so far. Even though our dependent variable is imperfectly measured, even though every observation contains some noise, OLS still estimates the correct slope and coefficient on average. So the data is messier, the estimates are less precise, but they are systematically not wrong, okay? Or not systematically wrong. And this is why economists often proceed even when they know that Y is measured with error, provided the error is classical. So the slope is still trustworthy, it's just noisier than it would be with perfect data. Now, the measurement error in Y is relatively benign. The location of the error matters enormously. So we'll discover in the next video how the story changes dramatically when the measurement error occurs in the independent variable X. So stay tuned and I'll see you then.